All right, so very back of your review, this FRQ is modeled after FRQ4. So these directions that you see up here are the exact directions you will see on FRQ4. So because of that, it includes some stuff that absolutely won't be on your test tomorrow because we're only going through the end of Unit 2, but it refers to some trig stuff. But I do want to talk about these directions. So this says, unless otherwise specified, the domain of function f is assumed to be the set of all real numbers. Okay, so we're assuming that. If you have any angle measures, they're assumed to be in radians. Again, that will not happen tomorrow because that's Unit 3 and we're only going through the end of Unit 2. Solutions to equations must be real numbers, so there won't be any imaginary stuff here. And then this is real important here. Determine the exact value of any expression that can be obtained without a calculator. So this is a non-calculator section. And we're going to not worry about the cosine and sine inverse just yet because we'll talk about that stuff later, because that's not going to be on here. But I do want to look at this, log base 2 of 8. Okay? Log base 2 of 8 is not completely simplified. And you can evaluate that without a calculator. I can rewrite this as log base 2 of 2 cubed, right? And then that 3, that exponent gets to come out front, and log base 2 of 2 takes care of itself and becomes 1, so my answer is 3. So log base 2 of 8 is 3. That is something that you are capable of simplifying, okay? We all good on all that? All right, so then unless otherwise specified, we have to combine terms and rules for exponents. So that's combining your like terms. And then let's look at this one because that applies here. Natural log of 3 plus the natural log of 5 will become the natural log of what? 15, because we multiply. Right? And then for each part of the question, of course, show your work that leads to your answers. That doesn't necessarily mean that you have to show every single step. I'm not really going to skip steps as I go through it because I don't want to lose anybody. I also think sometimes it's better for you not to skip as many steps as some of you want to because that's where our careless errors happen. Okay. All right, and this is formatted to actually be done on a separate sheet of paper. I probably should have reformatted it before I gave it to you, but I didn't, so here we are. My work's going to be all over the place, but hopefully you'll be able to figure out what's going on here. All right, so functions g and h are given here. The first part says we're going to solve g of x equals 1. So I'm going to take g of x, log base 3 of x plus 2 minus log base 3 of x plus 1, and I'm going to set it equal to 1. Okay. Now I am going to combine the left side, and this is going to give me log base 3 of x plus 2 over x plus 1, and that equals 1. Right here, right now, can I drop the log? No, and that was a huge mistake that a lot of people made on that last test. Y'all were willy-nilly dropping logs everywhere. I don't even know what was happening. So I need to rewrite this as an exponential, or the other way I showed you, which I regret not doing from the beginning, but again, here we are, is that, I can do 3 to the first power equals this and go around in a circle, but the base is 3. So if I make both sides exponents and I make 3 as the base, like this, then 3 and log base 3, those take care of each other. So I get x plus 2 over x plus 1. And that equals 3 to the first power, which is 3. Okay, we good on that? Now I have so I haven't dropped my log. I legally did stuff, right? Now I'm going to just, no, it's just algebra. So x plus 2 equals 3x plus 3. So that's going to give me a negative 1 equals 2x. So x equals negative 1/2. So x equals negative 1/2. And it says in the domain of G. So we have to check it. Negative 1/2 right here would still give me a positive number. Negative 1/2 right here would still give me a positive number. So we're good. Any questions so far? All right, good deal. And hopefully, if you actually did this ahead of time, you are happy with what you did. All right, so now let's look at this one. H of x equals 3 to the 4th. So here's h of x. 9 to the 2x power times 3 to the 1/2 power over 3 squared equals 3 to the 4th. Okay. Now, I would like for all of the bases to be the same. So that 9, I'm going to make it into a 3 and make this 3 squared to the 2x power times 3 to the 1/2 power over 3 squared equals 3 to the 4th. Okay, everybody with me so far? So over here, this can become 3 to the 4x power, 3 to the 4x times 3 to the 1/2. And then I'm going to multiply both sides by 3 squared. And that's going to give me 3 to the 4th times 3 squared. Everybody with me so far? Nobody's dropping nothing because I don't have singles on either side. I am multiplying two terms with the same base. What is my rule for the exponents? Add. I know you know that. Most of you did not actually do that on the last test. So I'm going to ask again, and you're all going to answer me. When I multiply two terms with the same base, what is my rule for my exponents? Add. Okay. So then I can change this to 3 to the 4x plus 1/2 power equals 3 to the 6th. So now I can basically just take the exponents. They have to be equal. So 4x plus 1/2 has to equal 6. Well, I need to subtract 1/2 from both sides. 6 can become 12 over 2. So 12 over 2 minus 1 over 2 will give me 4x equals 11 over 2. Then I have to divide by 4. Dividing by 4 is the same as multiplying by what? 1/4. So that would give me x equals 11 over 8. So x equals 11 over 8. What questions you got? We good? All right, now let's look at some wording here. On these first two, it says solve and solve. And we did. X equals, right? These say rewrite, rewrite. It says nothing about solving anything. So my rules change just a tiny bit because I'm not balancing the equation. Like whatever I do to one side, I'm doing to the other. Because I'm simplifying, I'm not solving. So always make sure you know what your goal is here. All right, so let's look at this little BI here. And I want, it says, right, j of x is an expression. It even tells you what it's supposed to look like and what your base is supposed to be. Well, I don't have to guess, where a and b are constants. So j of x is equal to, and then I'm going to make that 9 into a 3, so 3 squared to the x plus 4 power times 3 to the 4x minus 1 power all over 3 to the x power. Everybody with me so far? All right, in the numerator, I'm going to make this, I'm going to fix this here. So this gives me 3 to the 2x plus 8 power times 3 to the 4x minus 1 power all over 3 to the x power. In the numerator, I am multiplying two terms with the same base. What do I do with the exponents? I add them. So here, my base is 3. I'm going to add these two together, so that's going to give me 6x plus 7. And then I have 3 to the x in the denominator. Everybody with me? I am dividing two terms with the same base. What is the rule for the exponents? Subtract them. So this is going to be equal to 3 to the 5x plus 7 power. So then j of x, because he has a name, is equal to 3 to the 5x plus 7 power. What questions do you have? I saw you squinting. Can you read everything? Because I was trying to write. It's hard to write small up here. Could you read my stuff? Okay. We all good? All right. Now, we're going to rewrite k of x. So for k of x, if you have multiple logs that you're going to combine into one, I think it's a good idea when you do the combining to put it all in one step. But you can't do that until you have log, log, log. Like I have a 3 in front of here. So this 3 is going to have to become an exponent. The 1/2 is going to have to become an exponent. And then that third term is fine. So k of x equals natural log of x cubed minus natural log of x plus 4 to the 1/2 power minus natural log of 2x minus 1. Now we are ready to combine. So k of x is equal to, then I'm going to have natural log of some sort of fraction. If the log is positive, which this is the only one that's positive, then the argument goes in the numerator. If it is negative, like this one, the argument goes in the denominator. And then this one's negative, so this argument also goes in the denominator. And then I'm done.
Would the x plus 4 mark, if it was marked with like a square root?
That would be fine too. Whether you did square root or 1/2, you'd be totally fine either way. Okay, good question. Anything else? All right, good deal. So all of this stuff so far, I think, is totally fair, totally doable on what we've done. I think the last part's fair too, but I do think that maybe you weren't comfortable getting through it necessarily because you haven't necessarily done an equation exactly like this before, but you have done equations like this before. I think sometimes you just don't know it. But here's the thing. It is impossible for me to give you examples of every single thing you could possibly see. Okay, this is just impossible. So, but remember that everything you should have the skills and the knowledge to do. So when you know that and it looks way out there, then you need to kind of dig deep and like, what can I relate this to? Why should I know this? What does this apply to? That sort of thing. So let's read this. It says, find all input values. So we're looking at m here, right? Input. So in this case, my input is x. In the domain of m that yields an output, in this case, my output is m of x, output value of 4. So basically, it's telling me m of x equals 4. So I'm going to take natural log of x squared minus 3 times the natural log of x equals 4. Now, I would much rather you have no idea what to do than to make up math. Okay, that's always more important there. But I want you to look at this. And when you get stuck on things, I want you to ask yourself the same questions I ask you. What does it look like? Do you know anything about it? Like, I know, forget the log part. Okay, yes, I know there's a log in here. It's a log equation. But aside from log, what type of equation does it look like? Does it resemble? That you have seen like this before if those weren't really logs. A quadratic, exactly. I got something squared, right? My highest exponent is squared. It could possibly be a quadratic. So rule number 1 on a quadratic is don't make up math, right? Rule number 2 is to do what? Set it equal to 0. So natural log of x squared minus 3 times the natural log of x minus 4 equals 0. So see, I have something squared minus that something minus a constant, okay? Set up just like a quadratic. Do we all see how it's a quadratic? Okay, now I could factor it just like it is, okay? But I think that that's where it really starts to hurt your brain even more. So instead, we're going to take a page out of the calculus rule book, and we're going to do a little something called U substitution, which you're going to do a ton over there. And what that means is this. I would like to take the log out of it so it doesn't look confusing. So we're going to say U equals natural log of x. Okay? Then I'm going to actually substitute that in here and get U squared minus 3 times u minus 4 equals 0. Does that look a little less intimidating? Can you factor this? Good. So factor that. U plus 1 and u minus 4. We agree with that? So now next step is going to be pretty much exactly like what we did for quadratics when it wasn't a u thing. I'm going to get u equals -1 and u equals 4. The only difference right there is we would usually probably put like -1 comma 4, but I want these split up because I'm not actually done now. Everybody with me so far? Now, what does u actually represent? Natural log of x. So that means here when I substitute it back in, natural log of x equals -1. Natural log of x equals 4. This is not where I test it because I do have to test my values, but I don't have x equals yet because that's what I'm going for, right? And then here I can rewrite it, or like I said, that what's the base of a natural log? E. So if I make those exponents with the base of e, then here these take care of each other, so I get x equals, and that equals e to the -1 power. And I really shouldn't leave negative exponents. What does a -1 do to my term? Flips it. So that means I get x equals 1 over e. And then here, that takes care of itself, so x equals e to the 4th. And then when I substitute it in, I just have to make sure I'm taking the log of a positive number. Are those both positive numbers? Yep, then these are my two answers. Okay. And then I want to show you that we could have factored from here. And you don't have to use the u substitution, but we could have logs inside of a quadratic. We could have exponentials. We could have trig. We will have trig. We will have all that stuff. So it's fine just to factor it. And if you still just think about it as a quadratic, okay, when this was u squared, well, this is just natural log squared, right? So I have natural log of x here and natural log of x here. And I still need two numbers that multiply to give me a -4 and combine to give me a -3. And so I get this 1 and 4 here. And then I could just go directly to that step. So you don't have to use the u, but I do think, especially when you first start seeing weird stuff like that, it probably helps you. Okay? What questions do you have? Doable, but challenging, right? But was the rest of it all that challenging? Not really. Lots of room for mistakes. But if this is one, I think this ended up being 2 points. I don't remember exactly, but you know, even if you got the other 4 points, like, hey, that's something, right? And then if we can muddle through this, that's something too. Okay. What questions we got? Anything? All right. Alrighty, let's go back to the beginning. And I know it says ISN page, but you don't have to put this in your ISN. Okay, so number 1, the figure shows the graph of a logarithmic function h. Okay, so the graph is h. This is h of x. H of x. Says consider the exponential function k not shown given by k of x. So some of the question from the beginning was, how am I doing this? These are 2 different functions. We need to read that to make sure we understand. And then we understand that a log is the inverse of an exponential. It tells me that this is the log, and it tells me that this is the exponential, but I should be able to tell that this is the log from the graph itself. They are inverses of each other. So if I have my input is -1 for k, it would be my output here for h. I don't want to have to guess at a number, so maybe I'll skip that one for now. My input here is 0, so my output would be 0, and that would be 1. And then this one, input here is 1, so output here is 1. That makes this one 2. And then this is 4 and 8. Okay, and then I can't see my output of 4, but I can see what's happening here. I'm multiplying by 2 each time, so that would make this 16, and this would for sure be 1/2. It looked like about 1/2, but we shouldn't guess, right? Okay, so number 2 tells me the figure shows the graph of an exponential function f of x. So this is f of x, and that is my exponential. Consider the logarithmic function g, not shown, given by g of x, which are on the, nobody has asked me about this, which makes me wonder if we have actually even done this, or if we have paid attention to any of this, because I don't have a table that says g, it says k. That is a mistake, but I would have expected somebody to ask me about that by now. So there is your g. Okay, so if my output for my log is -2, that would be my input for my exponential. I feel like that would be a guess, that would be a guess. So let's look at my output over here is 0, my input, that gives me 1. And then when my output is 1 here, that's my input here, that would give me 3. Output is 2, so that is 9. Looks like I'm multiplying by 3 each time, so this should be 27. This would be 1/3, and this would be 1/9. Okie dokie. Let's look at 3. All right, so I've had a lot of questions on these as far as the little pictures go. So this is all about logs right here, but I'm going to talk about exponentials first because I think we're more comfortable with exponentials. Maybe they make a little bit more sense. So if I have, so you know your generic exponential looks something like this. So that would be like 2 to the x power. If I had this would be, one way to do it would be 1/2 to the x power. Okay? So those are exponentials. Then we know that the logs are inverses of exponentials. So your generic log, kind of the first thing you think about would be this. This would be like log base 2 of x. And notice how these two, when we change between these two, it's a reflection in the y-axis. If I have log base 1/2 of x, oh, I was trying not to draw too close, but of x, it's not calibrated on the side. This would end up being a reflection in the x-axis. So these reflect in y, this reflects in x. So that's kind of what our beginning looks like for that. So when I look at these over here, I've got, if I have log base 1/5, that's going to start off looking like this, right? So I start off looking like this, but then this is a reflection in the x-axis, which means it reflects it back up like so. So that function is increasing, so it's one of these two, and increasing at a decreasing rate or increasing rate. So for that, I need my fun chart. So if my rate's increasing or decreasing, I'm looking at the concavity. This is concave down, which means my rate is decreasing. So this is f of x. All right, so then log base 4. Log base 4 would start off looking like that. All the 3 does is stretch it. It doesn't change any of the attributes that we're looking at. But this negative, when I make x negative, I am reflecting in the y-axis, so it would look like that. That is a decreasing function, so it's one of those two. It is concave down, so it is decreasing at a decreasing rate. This is g of x. All right, so log base pi. Well, that, it's pi, whatever. That's greater than 1. It's going to look like this to start with. Looks like this. And then that negative means that we reflect in the x-axis, so it ends up looking like that. That is a decreasing function. It is concave up, so it's decreasing at an increasing rate. this is h of x. Then I'm not just going to plug in k of x in the first one. I'm going to make sure that I agree with it, because if not, then I got to go back and recheck some other things. So log base 1/2 starts off looking like this. That negative is going to reflect it in the y-axis, so it looks like that. That is an increasing function. It is concave up, so it's at an increasing rate. This is k of x. Okay. All right, 213. The function f is given by f of x here. What input value in the domain of f yields an output value of -11? Okay, in this particular case, because of what I have here, the input is x, the output is f of x. So it's telling me f of x is -11. Great. So let's then go and say, all right, I'm going to take -15 times log base 8 of x minus 1 minus 6 equals -11. All right, first step, just like solving any equation, is going to be to move that 6. So I've got -15 times log base 8 of x minus 1 equals, I'm going to add 6 to both sides, that's a -5. All right, so then the next thing I do, now this -15 could become an exponent, but that seems like a nightmare. So instead I'm going to divide both sides and get log base 8 of x minus 1 equals -5 over -15. That's going to reduce to 1/3. So log base 8 of x minus 1 equals 1/3. Okay. I could rewrite this in exponential form. Well, I'm going to rewrite it. I keep saying I could. I'm going to rewrite it in exponential form. I could do 8 to the 1/3 and go around in a circle. But remember, other thing that I've shown you is that the base is 8. So I'm going to make these both sides exponents with my base 8. And when I do that, these take care of each other. So I'm left with x minus 1 equals 8 to the 1/3 power. 8 to the 1/3 power is the same as the cube root of 8, something we should know. So x minus 1 equals 2. I add 1 to both sides, x equals 3. Then we check it, okay, because it even says in the domain. So I take my 3. 3 minus 1 would give me a positive number, so I like that. That's my answer. Okay. All right. The function g is given by this right here. Find the x-intercepts of g of x. Okay, x-intercepts occur when y is 0. So when g of x equals 0. So what I'm looking for. So I'm going to take log base 7 of 3x plus 2 plus log base 7 of 2x plus 3. And I'm going to set that equal to 0. On the left-hand side, I need to combine my logs. So this is going to give me log base 7 of 3x plus 2 times 2x plus 3. Okay, all of that there. And that equals 0. I absolutely, positively cannot just drop the logs. Okay, my base is 7. The base is 7, so I'm going to make these exponents with a base of 7. These take care of each other. I'm left with 3x plus 2 times 2x plus 3 equals 7 to the 0 power is 1. Now on the left-hand side, I need to multiply that together. So that's going to give me 6x squared, and then plus 4x and plus 9x would be plus 13x plus 6 equals 1. Then I'm going to be able to subtract 1 from both sides. So 6x squared plus 13x plus 5 equals 0. I need to factor. A is not 1, so I can't jump to the equal signs. I need to factor by grouping, and 6 times 5 is 30. So I need two numbers that multiply to give me a positive 30 and add to give me 13. So that'll be 6x squared plus 10x plus 3x plus 5 equals 0. I got this and this. So I can factor out at 2x, leaves me with 3x plus 5. Factor out at 1, 3x plus 5 equals 0. So 2x plus 1 times 3x plus 5 equals 0. So I get that x equals a negative 1/2 and a negative 5/3. And then I need to check them, right? So negative 1/2 in here would give me negative 3/2. Negative 3/2 plus 2 is still positive. Negative 1/2 right here would give me a negative 1. Negative 1 plus 3 is still positive. Negative 5/3 right here would give me a negative 5 plus 2, which would be a negative number. So I don't like this one. Negative 1/2 is my only answer. Okay. All right. Now we are going to expand the logarithm fully using the properties of logs. Now this whole idea of fully is important here. Express your final answer in terms of the log of x, log of y, and log of z. No exponents. Okay. When you split these, I highly suggest you start by doing just the splitting all in one step. Okay. So when I do that, everything that is in the numerator has a positive log. So that's log of y. The x is in the denominator. So that's going to be minus log of x. This is also in the denominator, so minus log of the cube root of z squared. Okay. Now, these first two terms are fine, but this I got to fix. Okay. So the cube root of z squared is the same as z to the 2/3 power. Okay. So instead of this, I could have z to the 2/3 power, which means when I actually write out my answer, I get the log of y minus the log of x minus 2/3 times the log of z. And that is my answer. All right. Consider the functions r and q given by these two equations. In the xy plane, what is the x coordinate of the point of intersection of the graphs? Remember, where two graphs intersect is where they have the x and y in common. These are their y values, so I can set this part equal to this part. So I'm going to get 32 to the x minus 5 power equals 8 to the 2x plus 3 power. The best way to handle this is by getting common bases. I know that 32 and 8 are both multiples of 2. So 32 is 2 to the 5th. So 2, 4, 8, 16, 32. Okay, so 2 to the 5th to the x minus 5 power equals 2 to the 3rd to the 2x plus 3 power. So that gives me 2 to the 5x minus 25 power equals 2 to the 6x plus 9 power. Now that I have common bases, I can just take the 5x minus 25, set it equal to 6x plus 9, and then this will give me x. I subtract that over there, negative 34. And then I don't have to check it because it's an exponential, not a log. So, all right. The function h is given by f of t. Oof. Yeah, somebody did ask me about this one, and I didn't tell you to fix this. This should say the function f. So obviously the function f is given by this. The function g is given by this. This is what h is. H is f of g of t. I highly suggest that if you see something that looks like fog, that you rewrite this as h of t equals f of g of t. I think that helps you make sense of that, okay? So I'm looking for h of t. Now I know what to do. This tells me that g of t goes inside f of t. So that means it's going to give me the natural log of e to the 9t squared power. So sometimes I just say, hey, this takes care of this, but let me just show you what's really happening here. This is my exponent. It gets to come out in front, 9t squared times the natural log of e. Now, you got to be careful with your wording here, because I keep hearing people say they cancel each other out. I mean, and I might even say that sometimes, but we got to be careful with that, because what this really equals is 1. And since I'm multiplying by 1, it's kind of irrelevant. But if I was adding that, it wouldn't just disappear. And that's what a lot of y'all did on that last test. So what we end up with here then is that h of t equals 9t squared. Okay. All right. The function h is given by h of t right here. K is given by this. This is g of t, and I want g of t. So really, g of t is equal to h of k of t. All right. So I'm going to take k of t and put it into h of t. And I think, it might be nice to condense k of t before we do that. I mean, you don't have to, but if you look at what's about to happen, this whole thing right here is about to become the exponent over here, and then I would have to condense it. So I could start off by just kind of fixing k of t a little bit. So let's do that. Let's say k of t equals, I'm going to make this an exponent here, and I'm going to make this an exponent here. So I get log base 5 of 4t squared to the 1/2 power minus, I'm running out of room because I'm writing too big, log base 5 of 3t squared. I don't know why it's like not calibrated on the edges. It's weird. All right, so this 1/2 is the same as a square root, and it goes over this whole thing right here. So this is also just log base 5 of 2t minus log base 5 of 9t squared. So I'm kind of going backwards here. So then I'm going to go here. So that means that k of t is equal to log base 5 of, and I can condense those and put 2t over 9t squared. So really k of t is just log base 5 of 2 over 9t. So now that I have simplified that, because I think that will make my life a little bit easier, now I'm going to put it into here and actually do this. And this will give me 5 to the log base 5 of 2 over 9t power. That 5 to the log base 5 takes care of itself there, and you get that g of t equals 2 over 9t. And that is your answer. Okay. All right. So then we have a data set that appears exponential, is modeled by the function h of t. The data are represented using a semi-log plot, where the vertical axis is logarithmically scaled with the natural logarithm. Find the linear model for the semi-log plot in the form y equals mx plus b. All right, so we have, we know that if we have exponential data, it appears linear on our semi-log plot. So remember that, okay? And I'm going to take this, and it says to use y equals mx plus b. So I want you to think about this as y equals 2 times 8 to the x power, right? And I'm going to linearize that data, which means I'm going to take the natural log of both sides. So this is going to give me the natural log of y equals the natural log of 2 times 8 to the x power. I cannot bring the x out in front as an exponent because it's only on the 8, it's not on the 2. Okay, and I'm taking the natural log of this whole thing right here. But I can split that, and I can get the natural log of y equals the natural log of 2 times, or plus, I'm sorry, natural log of 8 to the x power. So then natural log of y equals natural log of 2 plus x times the natural log of 8. So if we want it in this form right here, then I could, we don't necessarily have to mix it up and rewrite it, but we can see that this is your mx, so your slope is the natural log of 8, and your y-intercept, I don't like calling it b because of other things, y-intercept is the natural log of 2. I also want to remind you that you can see these in two different forms. You can see it where this says the natural log of y, or sometimes this just says y, but it has to do with whether or not it's going on a semi-log plot, so just don't let that confuse you, okay? All right. Now we're going to consider the constant function, f of x equals -4. It's a constant function because that means y equals -4, and it would look like this, right? And function g given by this right here, h is g of x minus f of x. What input value, which would be x, and the domain of h yields an output value, h of x, of 7. Okay? So h of x, which is 7 is equal to g of x, which is -2 log base 4 of x, minus f of x, which is a -4. Right? So I just substituted stuff in. So 7 is equal to -2 log base 4 of x plus 4. Try to get x by itself. So I'm going to move the 4 first. I'm going to subtract 4 from both sides. I'm going to get 3 equals -2 log base 4 of x. That -2 could become an exponent, but because I'm solving, my other option is to divide, so I think I'd rather do that. So I'm going to get 3 over 2, and that'd be negative now, equals log base 4 of x. And then my base here is 4, so I'm going to make these exponents with a base of 4. And this will give me 4 to the -3/2 power equals x. Now, I can't leave it like that. I've got to simplify this all the way. Okay, so let's do this step by step. The negative, well, let's leave the negative there for a minute. I want you to remember that you can break this stuff up. So this is like 4 to the -3 power to the 1/2 power equals x. Or I could think of it as 4 to the 1/2 power to the -3 power equals x. Those are the exact same thing. So let's think about, would it be easier to take 4 and cube it, or would it be easier to take 4 to the 1/2 power, which is the square root of 4? I would think I would want to do this one, okay? But either one of them are fine. You can do it in any order. This means the square root of 4. So I take the square root of 4 and I get 2. That now means that x is equal to 2 to the negative 3 power. 2 to the third power is 8. That negative gives me the reciprocal, so x is 1 over 8. And that's it. We're back to the beginning. I know you can do well on this. I know you can make yourself proud and do better than you did on the last Unit 2 test. You got this.